We continue to the last subchapter of the DC drive, which is the electrical braking. Okay, electrical braking is usually employed in applications to stop a unit driven by motors in an exact position or to have the speed of the driven unit suitably controlled during its deceleration. Electrical braking is used in applications where frequent, quick, accurate, or emergency stops are required. Electrical braking allows smooth stops without any inconvenience to passengers. Okay, for example, when a loaded hoist is lowered, electric braking keeps the speed within safe limits. Otherwise, the machine or drive speed will reach the dangerous values. When a train goes down a steep gradient, electric braking is employed to hold the train speed within the prescribed safe limits. Electrical braking is more commonly used where active loads are applicable. In spite of electric braking, the braking force can also be obtained by using mechanical brakes. Okay, the main disadvantages of the mechanical braking are first, it requires frequent maintenance and replacement of brake shoes, and braking power is wasted in the form of heat. Okay, in spite of having some disadvantages of mechanical braking, it is also used along with the electric braking to ensure reliable operation of the drive. It is also used to hold the drive at a standstill because many braking methods do not produce torque at standstill condition. Okay, there are three types of electric braking in a DC motor. We have a dynamic braking or static braking, plugging or counter current braking, and regenerative braking. Okay, we go to the dynamic braking of DC machine. Okay, the dynamic braking of DC machine employed in such cases where the kinetic energy of the rotating parts is dissipated in an external resistance. Okay, now we consider a shunt motor. Okay, this is the shunt motor whose field field is directly connected to a source ES. Okay, and armature, this is the armature, is connected to the same source ES by means of a double throw switch. This we call a double throw switch, and the switch connects the armature to either the line, okay, or to an external resistor R. So when the motor is running normally, the direction of the armature current I1, okay, and the polarity of the counter EMF E0, okay, as shown in this diagram. Okay, so we neglect the armature drop or IR drop. So when we neglect this armature drop, you get E naught equal to ES. Okay, means that RA kita neglect. Okay, IA equal to 0. So we get E naught equal to ES. Okay, and then if we suddenly open the switch, okay, you look at this figure, we open the switch, the motor continues to turn, okay, but its speed will gradually drop due to friction and windage losses. Okay, on the other hand, because the shunt field is still excited, induced voltage E0 continues to exist, falling at the same rate as the speed. In essence, the motor is now a generator whose armature is an open circuit. Okay, and then you look at this diagram. we close the switch on the second set of contacts, okay, so that the armature is suddenly connected to the external resistor, this resistor. Voltage E0 will immediately produce an armature current I2. Okay. However, this current flows in the opposite direction to the original current I1. It follows that a reverse torque is developed whose magnitude depends upon I2. The reverse torque brings the machine to a rapid but very smooth stop. Okay. In practice, resistor R, okay, is chosen so that the initial braking current is about twice the rated motor current. And then the initial braking torque is then twice the normal torque of the motor. Okay. As the motor slows down, the gradual decrease in E0 produce a corresponding decrease in I2. Okay. Consequently, the braking torque becomes smaller and smaller, finally becoming zero when the armature ceases to turn. And then the speed drops quickly at first, okay, and then more slowly as the armature comes to a halt condition. So the speed decreases exponentially, okay, somewhat like the voltage across a discharging capacitor. Okay, consequently, the speed decreases by half in equal intervals of time t0. Okay, at time t0, the speed decreases half of the rated speed. And to illustrate the usefulness of the dynamic braking, we can compare the speed curve for a motor equipped with dynamic braking and one that simply calls to a stop. Cause means the braking is depends on the friction and windage losses. Okay, so this is the equation, okay, by referring to this figure. Okay, you look at this figure. Okay, so from this figure, okay, you have a E naught. So E naught is EB. So means that EB equal to E naught. And then we have a RA. So means that RA here. Okay, we have a RA. And then we have a RDB. So R equal to RDB. And then when you apply KVL here, you get EB IA equal to EB over RA plus RDB. And then we know that E equal to K flux omega. So we get this equation. And then this negative sign shows the armature current is reverse. Okay. Okay, then we have an equation for torque equal to K flux IA. And then from that equation, you can derive this equation. Okay, dynamic braking and mechanical time constant. Okay, I have mentioned that the speed decreases exponentially with time when a DC motor is stopped by dynamic braking. So we can therefore speak of a mechanical time constant T in much the same way we speak of the electrical time constant of a capacitor that discharge into a resistor. So in essence, T, okay, T is the time it takes for the speed of the motor to fall to 36.8% of its initial value. However, it is much easier to draw the speed time curve by defining a new time constant T0, which is the time for the speed to decrease to 50% of its original value. Okay, there is a direct mathematical relationship between the conventional time constant t and the half time constant t naught. So it is given by this equation. Okay, then we can prove that this mechanical time constant is given by this equation, where J is the moment of inertia and 1 is the initial speed of the motor when braking start. Okay, and P1 is the initial power delivered by the motor to the braking resistor. And then we have a two constant 131.5, okay, and 0.693.